Hello world, it's Dr. D from ACU. Let's talk about 2D motion. So instead of moving in just X or in Y, we're going to start traveling across the second dimension. So I'm going to have motion that's happening both horizontally and vertically at the same time. And there's one simple trick that makes this all possible. The key concept for this is that the X and Y motions are completely independent of each other. Now, I'm going to tell you this, you're not going to believe it at first. With enough practice, you'll actually get the hang of it. But the reality is, the concept is simpler than you want it to be. Your brain tries to tell you that this is a really hard thing, but the truth is, all we have to do is do our problems once vertically and once horizontally, and we're done. If you can copy and paste, you can do this material. Now, the X and Y components are independent, but if I do ask you for a vector like a total displacement or a total speed, that will depend on both the X and Y components. There will be sometimes we have to put the pieces back together. So to review, I'm going to take the four kinematics equations. These are my big four equations for constant acceleration. And I'm just going to copy and paste this. I'm going to have one set for X and one set for Y. And I'm going to do this because the X and Y motion is completely independent from each other. It can help a lot to think about some kind of rocket ship where I've got an X thruster and a Y thruster. So if I do this once, I've got an X rocket that's giving me velocity and acceleration in the X direction. That's making me displace in the X direction. So I have one set of my equations that have everything with X. So for notation, I'm now going to have AX is my X acceleration, Vx is my final X velocity, V naught X is my initial X velocity, and X is my displacement in the horizontal direction. Now I do this once again with my Y rocket turned on. Y acceleration, Y initial velocity, Y final velocity. Just a copy and paste job, turned all the X's into Y's. So I can put those bits together. And the trick is, again, you're not going to believe me at first, but eventually you'll come around. The X part of the motion is independent from the Y part of the motion. The X part occurs exactly as it would as if Y didn't occur at all. So think about it this way. What's happening in the X direction does not depend on whether or not this Y rocket is turned on. It simply doesn't care. What happens in X is only affected by the X rocket. What happens in Y is only affected by the Y rocket. So these motions are independent, and we can treat them that way. Now, for most of the problems you're going to do in this section, we're going to make life so much easier for you and solve a really interesting problem. We'll talk about projectile motion. So let's think about an object now that is in free fall. So the only acceleration that's happening is gravity. But as you know, gravity moves straight down. So I'm going to have acceleration from gravity in the y direction, and then we'll assume that there's no acceleration in x. So I've got some basketball or cannonball or satellite that's moving, no acceleration in x, acceleration of negative 9.8 in the y direction. And it turns out these problems are really interesting and totally doable. The nice thing about having no acceleration in x is I take my list of my equations that I've copied and pasted. So now I have two sets of my big four equations, one in x and one in y. But if I say my acceleration in x is 0, that goes away, and every term with an ax goes away. My final velocity is the same as my initial velocity in x, so I can ignore that variable. And all that happens in x now, everything goes away except for one little term. X equals v naught xt. Distance equals rate times time. Meters equals meters per second times second. So with projectile motion, x is really, really easy. And all the interesting stuff happens on y, where that's accelerated. So I'll do one example to show you how this works, and then a quick summary, and we are done. Okay, So a place kicker kicks a football at an angle of 40 degrees, and the initial speed is 22 meters per second. How far does it go? So for these problems, I need to think about this remembering that the x and y motions are completely independent. So to know how far the ball goes, well, in x I only had one equation. X equals the x velocity times time. So to figure out how far it goes, I have to know the time that the ball is in the air. Well, the time that the ball is in the air only depends on the y motion. So the only variable that really matters here is how high did I start and what was my y velocity, because then it's the acceleration acting on that makes it come back down to the ground again. So our plan's pretty simple, a two-step problem. First, we're going to look at the y motion to figure out how long the ball is in the air, and then we'll use that and the x velocity to figure out how far the ball traveled, so what's its final range. The first step in any problem is to get organized and write down what you know. It is so important to get you unstuck at the beginning. Do not skip this step. So all I was given was that my ball moves with the speed of 22 meters per second at an angle of 40 degrees. And if I just draw a simple diagram, I can see that this speed has both an x and a y component. So if I'm going to be breaking this up into x and y motions, I need to find the initial velocity in x and y, and so we can do that from trig. If I find my initial x velocity, well, here's my x component. I'm adjacent to theta, so I'm going to use cosine. So 22 cosine 40, 17 meters per second. My y component is opposite from theta, so I'm going to use sine. But if I used cosine here, I'm going to use sine here. Make sure my calculator is in degrees mode. 22 sine 40 is 14. As a quick reality check, if my angle is less than 45 degrees, I'm going to be going faster in x than in y, and that works out. Okay, so now let's write down what we know about the x and y components. So my problem was to find the displacement in x. What's the total range? How far does it travel? I don't know about y yet. My acceleration, it's a projectile motion problem, so 0 in x, negative 9.8 in y. We just found the initial velocities. Because there is no acceleration in x, its final velocity is the same as its initial, but I don't know the final in y yet, and I don't know how long the ball is in the air. So the plan that we constructed on the last slide says I'm going to use the y motion to find t, then I'm going to use t and this velocity to find the x displacement. Now we can look at the vertical motion to find how long the ball's in the air. There's lots of different ways to solve this problem, but one way that we can approach this is to say, at what time t is the ball back on the ground? So once the ball hits the ground, its height, y, is 0, and I still have my acceleration and my initial velocity, and that gives me enough information that I could solve for time. So now I go back to my list of my big four kinematics equations, and I find the one that has these four variables in it. So let's choose this one. Y is v naught yt plus 1/2 aat squared. I need to solve my equation for t. Now normally that would be really hard with a t and a t squared. It would be a quadratic equation, maybe even a quadratic formula thing. But fortunately we can get out of this because y is equal to 0. That makes this equation a lot easier to solve. So now I've got a t in both terms here on the right, so I can divide both sides by t and get rid of one of those. Now what that extra t is doing here mathematically is telling us that another solution to this equation is t equals 0. And you know what? The math is right. The ball is in fact on the ground at t equals 0, just not the solution I care about. Okay, so I'm going to divide both sides of my equation by t and cancel one of these t's out of both terms. So that's done. Now I have something that's pretty easy to solve for my time t. Just going to move this term over here, and then we can be all set up. So, solving this guy for time t, negative 2v over a. If you ever have concerns whether or not you've messed up the algebra, stop for a second and think about units. Meters per second divided by meters per second squared, well, that per second squared in the denominator ends up canceling out the meters per second and giving me an extra seconds left over in the numerator. So my time does in fact have units of seconds and everything's okay. I've got this minus sign that might make me a little nervous until I realize that my acceleration is negative as well. So a minus sign and a minus sign here will give me something positive, which is good. If I'd gotten a negative time, I might be afraid that I've made a mistake somewhere. Okay, so anyway, write my equation with my numbers plugged in. Negative 2 times 14 divided by negative 9.8 equals about 2.9 seconds. As always, I stop and think if my number makes sense. And we're kicking a football, so yeah, a hang time of a few seconds. I am okay with that. So we've now figured out how long the ball's in the air. Let's use that to solve our final problem. So in x, I now know everything except for how far it goes. The acceleration, the velocity, and the time. But we really only have one equation in x. That's x equals vt, because there is no acceleration. Distance equals rate times time. Meters equals meters per second times seconds. These equations are not hard to memorize. So x is 17 meters per second times 2.9 seconds equals positive 49 meters, and that positive means that it's going to the right. Now, we are not done with this problem because we always end everything with a reality check. Does my answer make sense? Have I messed up somewhere? If I'm kicking a football, 49 meters, that's about a little over 50 yards. That's a totally reasonable distance for a place kick. Now, if I go through an exercise like this, I can figure out anything that I want to about projectile motion. So here's a little summary table and approach of how we did it. So we solved the hang time, finding the t when y was equal to 0. We found the range. You could also say find the height. One clever way to do this is to think about when the ball is going up at the very highest peak at the top of its trajectory, the y velocity is 0 because the ball is in the process of stopping and turning around and coming back to Earth. So I can write down the big four equations and solve for a y when the velocity in the y direction is 0. And when you do that, you get some equations. We've already looked at these two, but this is the height equation. And you can always use these to make your life a little easier. So that is all that we need for projectile motion. Same as motion in 1D, except the x and y motions now happen completely independently of each other. Most of the examples you'll see are projectile motion like the one we just did. So if you can do it in 1D, you can do it in 2D. And if you can do it in 2, it's easy enough to go to 3, or 4, or 5, or 12 if you want. The math is all the same. Also, don't forget that everything is a vector, so don't forget the minus signs, pay attention to the directions, and everything will work out just fine. Happy projectile motioning, everyone. Thanks for watching.